Hello? Okay, I think it's fixed now. So did everyone go to this notebook? Everyone have this notebook opened?
No.
Okay, so let me go back to the link. Elliot, is the sound working well?
Yeah.
Okay. Okay. So here's the link.
Okay. Do I need a GitHub account?
No,
Oh.
you shouldn't need one. Okay, all done? Okay, and then
Sorry, how do you spell your name?
Haidy Giratallah.
Okay.
And then just click on the classification notebook. Okay, everyone here? And then click the Open in Colab. Let me open it in a new tab. Everyone following so far?
I don't have Wi-Fi. Is there like a temporary?
Yeah, that's why I asked in the beginning. Okay. Elliot, can you create a guest Wi-Fi? Okay.
It's okay. I'll see if I can get my phone to do that.
Do you have a Jupyter installed on your local? Okay, so you can just open a new notebook and then just code along. You don't have to be, this is just to make it easier. If you don't want to code along, we also have the notebooks solutions, so you can copy and paste. But I would rather, okay, and then the next step is to connect your notebook. So if you're working on the local host, you just need open your Jupyter, a new notebook, and just start coding. But here, if you want to connect this notebook, you just click connect here, and it will host it on Google servers, and then you can start typing code. All good? Okay, since most people are beginners, so this is an interactive way to code Python. So you can, this is called the code cell. So you can add code chunks or code cells by here, do it by clicking here, or you can add markdown or text here. You can also, if you can't open this notebook or it's not connected this way, you can always do file and then copy, save a copy in your drive if you have a Google Drive, and then you open it from there and connect it from there. You can also download it, download the notebook itself, or download the Python code. Yeah. Okay. So yeah, thanks everyone for being patient. So let me first introduce so what we were trying to do here. So machine learning is now becoming more and more popular. Of course, you hear a lot about machine learning research and AI and stuff. So, but in fact, it comes down to very simple problems. So these are one of the simplest examples. So more broadly, we have two types of machine learning: supervised and unsupervised. So supervised machine learning would be that you have you tell the model which is what is important and what is not important, and you keep trying to label things. So you have labels, you have prior knowledge that can infer what are the variables or features that might be of importance to do a prediction for your target. Unsupervised, you have no clue how to figure out this problem, or how to classify, or how to tell predict if a person has a disease or don't have a disease, and you have no idea what features, and you don't even have the labels who's diseased and who's not. Or so you can do unsupervised machine learning and let the model clustering, for example, is one example of unsupervised. You can let the model tell you, okay, these groups seems to be closer to each other, and these groups seems to be different than the previous group. So it can, that's a different problem than today's problem. So today we're doing supervised machine learning. Supervised machine learning is divided into mostly two kinds of problems. So classification and regression. So if you, it basically comes down to what kind of target are you trying to predict. So if you're trying to predict classes, so you have disease, non-disease, like we will have here, then it's a classification problem. I'm trying to classify, trying to generate an equation or a model that that can tell me if I give this person's height, weight, diagnostics, whatever features I will put, it will tell me if this person has the disease or don't have the disease. This is a classification, a 0-1 thing, a binary thing. But if we want to have, if we have a continuous measure, continuous variable, and you want to predict exactly the risk or how much exactly you want to predict a continuous number, or if our target simply is a continuous variable, then you would have a regression problem. So first, let's go through the classification example. So here we have, we will load some breast cancer data. And we usually first, when trying to run anything in Python, we try to, we first import some packages. So of course, people have been doing this for so many years, and a lot of the problems now became easy because of people putting up together the similar functions or things that we would need and making a library out of it. So we will import the libraries that is needed, so you don't have to code from 100% from scratch. You can always start where others have, like, you know, standing on the shoulders of giants and stuff. So I will be importing these libraries, and you can type or you can watch. So the first library, importing NumPy. So importing NumPy is just a library of numerics dealing with math and numerical values. And when we say import some library as something, so this is usually just for ease of abbreviating. Instead of me, if I'm calling this library, instead of typing NumPy each time, I would just type NP, and this would save me the trouble of typing the whole thing. And sklearn or scikit-learn is our main library today, because this is a very nice, widely used library for machine learning stuff. So, but it's a huge library. So usually we will start importing bits and pieces as we need it. So you have the option to import some of the library, some aspects of the library. You don't have to import the whole thing. So that's why I have from sklearn. So that's the whole library, and then .dataset. So now I'm just importing the data set that I'm using. From this, import make regression. Okay, so this will become clearer as I go. And then I'm importing also matplotlib. So this is just a plotting platform package for just doing the plots. If you want to plot something, Seaborn is also a nice interface of a plotting library that is built on top of matplotlib. And then finally, pandas is the DataFrame handling package or library. And so you can run this cell after typing, either by clicking, run anyway. So either by clicking Shift Enter or by clicking the tiny play button that was here. But for ease, just Shift Enter. So now if nothing happens, then it ran because it's just importing. I'm not asking it to output anything, so it won't do. Unless it gives you some kind of an error, then there was a problem. But if it didn't give you anything, it's not a bad thing, it's a good thing. This is just an extra cell. We don't need that. So we want now to, one second. Oh, sorry, I'm starting the classification. I was starting with the, one second. We'll import one more thing. Classification. Okay, so we will be importing also from sklearn datasets. So let's leave this for later, it's fine. I will just be importing make classification instead of making regression. And run this again. And in the second cell here, that's why I had the second cell, we will just set this plotting style as, using Seaborn. So I'm just identifying that on my main plotting style will be Seaborn. And this will also come clear later. So here we will continue, so getting the data set itself. So here's the link for the publicly available cancer data set in general. You can go there and explore what kind of data sets they have. So I will import this by also doing the same thing from sklearn datasets, import the load breast cancer. So this saves me the trouble from loading. Usually you load a CSV, you load a, you read CSV, you read something. So, but sklearn has a function already that can load this breast cancer data. So what I'm doing here is just importing this function and then saying that, okay, let's save this cancer as the load breast cancer data. And the next thing is that we will be taking a peek on this data set. So let me start by typing, so this data frame, so df, this is a variable. If you're not familiar with Python, this is a variable. So you can save a number, a list, data frame. You can save anything as a variable by doing this. And so here I'm just saving the cancer data that I loaded as a data frame, or like the normal CSV or sheets look that we are used to. So PD, remember this is the pandas library that I'm imported for handling the data frames. So I'm just telling pandas, so pd.dataframe, so make a data frame. And don't worry if this sounds too complicated. It's usually like a lot. If you have a CSV, you can just load the CSV directly. So far you can just copy and paste this. You don't need to fully understand that. But it's simply combining the cancer data, so the features that I want, and the target. So the target I will explain now once this comes up, and the feature names. So I'm just importing these features. So can you all see this? Do you need more time to type? All good? No? Okay. So the first line, I'm just saving the cancer data as a data frame. And then the second line, I'll just show the head or the first 5 rows from this data set. So if I run this, it will become more clear. So let me just do this so that it comes in on the same line. When you enter and it's still part of something, it's usually automatically intended, but intending is very important in Python. So what's part of what? So all of this is part of the data frame function. So it's aligned here. So this is just, all of this is just getting the data from the cancer database. And I saved it as a data frame called DF, just for short, okay? So DF is my cancer data frame. And when I do df.head, so head is a function that usually shows me whatever rows I want. So if I just run it empty, it will show me automatically the first 5 rows. And Python usually starts at 0, so it's 0, so that's my 5 rows. But if you want to specify something, you can, I want the first 20 rows, and then it will show you all the 20, or you want from the, you can check our other intro to Python lessons if you're not really familiar with how to manipulate data frames. So my main point here is just, so now we have this data frame, like we all, if you're in your lab, have an Excel file and you collected some data. So I have some cancer data being collected. So I have the mean radius of the tumor, I have the texture, the perimeter, the area, etc. I have so many features reported for this tumor. And then finally, or for each individual, so each row would be an individual. And then finally, which we combined over here, so the target, this is the target, this is the answer. This is basically what's telling me, is this person with all of these features diseased or not diseased? Like, does this person have a tumor or not? So 0 would be no, does not have the tumor. And then 1, I guess there, oh, here's the 1. So, and 1 would be the, with the disease or with the tumor. Okay, is it simple so far? Everyone following? Okay, I will take this as a yes. And okay, so a good idea is to always try to plot your data. Of course, this is not always feasible, but it's very helpful if you can see a simple scatter plot on how the data looks like, especially with your target. So now I want to classify 2 things. So I want to look at those 2 things, and I want to look for those 2 things, especially for the features that I think are most important in determining if this is a malignant tumor or not. So we will take an example. So we will try to do a scatter plot. So scatter plot, since we already loaded Seaborn and we set it as main, so we loaded as short for SNS. So we can save this plot as AX. So I'm saving the plot to a variable. So AX equals SNS, please plot me a scatter plot. And then what's in the scatter plot is my X axis will be the mean radius. So I think that the radius might be the radius of the tumor, may be a good feature. And I want also the mean concavity as my Y. So I just want to look at those 2 features using my data frame. And hue is just the coloring if I want to color by something else, which is in this case the target. So I want you to color the cancerous and non-cancerous samples differently. So I want you to color them by target. And then you can specify, there are so many color palettes of, or you don't have to say this, but if you want to get really neat and pretty, you can always add stuff to your plot. So I'm just using a deep palette. And finally, I'll just set the axis as row data plot. This is just the title. So this is just the title of my plot. So if you run this, it will show you, maybe I should zoom out a little. Can you still see, or is it become too small? Okay. So here's the, see, when I plotted, things became clearer. Okay, I might have a classification problem because I see that all the non-cancerous classified individuals are sort of clustering in a side that is different than the cancerous one. So I see a separation. If I see a clear separation, of course, there's still some overlap over here, which is okay in some, like, depending on the model that you will choose. But if you see some sort of a nice separation, then this is a very nice classification problem. And so what we will basically do is, like, we will try to make a line between here. So the classifier will simply be sort of some kind of a line here. that can separate. So if the person has a mean radius of 20 and a concavity of 0.2, then if I gave on a new person that I don't know if this person have a cancer or not, and I gave them those two inputs, it will tell me, okay, it's beyond that line, so it will be non-cancerous or not. So how do I start doing this? So one very so you can do this, of course, if you tried logistic regression before. That's one thing that you can try. But there's the thing that I wanted to teach today, a very more popular model that's being used, which is the support vector machines, or SVM. So it's of course there's a lot theoretical background to this type of models, but it's just simply it's one kind of model that will generate that kind of a line, and with the it's shown to be one of the most accurate ones in classification, since I will explain now, it takes into consideration another additional support vectors. So I will import this function, which is already someone else has written it, so I don't have to keep writing the equation. So I'm just importing the support vector classifier. So from the scikit-learn SVM, I will import the support vector classifier, and then I will say that my SVM is support vector. So I'm just using the kernel here as linear. So I'm just using a straight line. I'm not trying to do non-linear modeling. So I'm just specifying the kernel. And everyone following so far? Okay. Please stop me anytime. We have increased the session length specifically based on people's requests that they need more time to code along. So please stop me if you have any questions or you're lagging behind.
Is the code somewhere that we can look at?
Oh yeah, sure. So I have so if you open the link that I provided earlier, you will have, so there would be the same title but twice. So the one with code along is with the empty cells, and the one with without the code along is the one that has the code. So you can copy the code. So I'm copying, so I'm trying to save time to go into the regression. But yeah, if you want to type, just okay. So the next thing that we would want to do, and we should be doing all the time, is the splitting. So whenever you're trying to do a machine learning problem, remember that your outcome or your end goal is to generate a model that is good enough, that it's not overfit, and it's good enough to make predictions for any new data that you get, right? So to ensure this, you need to not train your model on all of your data. You need to have some kind of testing data. So you need to split the data that you have into training and test, and sometimes even split into a different validation tests. And there are so many types of like cross-validation, and we might get into the details if time permits when we get to the regression. But a general idea, if you don't want to get into more complicated splitting, you can just, a convention that is being used is to split 70-30. So 70% you would train your model on 70% of your data, and then leave 30% untouched. The model doesn't see, and then when you create the model from one, you predict or fit it into the remaining 30%, and then you see if the predictions are accurate since you already have the answer. So that's one way to evaluate your model. So here there's a nice way. Of course, there's a lot of ways you can do this, but a nice, easy way is to also import the test train split function. So from sklearn model selection, import the train test split, and then I will specify so I will say that my data frame, so this is just the way I'm naming it, so that the train, so underscore train, and the test, comma test will be my train test split from the main data frame. And I will say the test size is 0.2. So this is 20%. So 20% of my data will be testing data. And the random state is 20. So you can like just assigning the randomness, like you can play around with this, but just like I'm trying to make sure it's a random split. So I will run this. And now if I want to train my model, I will be using the df underscore train. And then when I'm trying to test my model, I will be using the df underscore test. Okay? So clear. So now if I want to check the size of my training and test data, I can simply try something as printing the size. So if I say print the size, anything in quotations is a string. So you can, I will just simply print this sentence, and then all of this is just a sentence. It will print it as is in the output, and then comma the training set dot shape. So print me the shape of this data set, and the shape of the train set, and the shape of the test data set. So if I run this, it will tell me exactly what's between the quotation, the string that I wrote, or the text. So the size of your training data X input features is 455 by 31. So this is simply the number of rows and the number of columns. So if you do the math, it's 20%, like 80 by 20. So the testing and the size of our testing data is, so I have 114 individual and the same 31 columns. So this is a nice way to always check that you didn't delete something from your data, or you didn't mistakenly remove a row or a column. So this is just by doing the shape function. And next we will start training our data, training our model. So we will start by, so if you remember, so the SVM, so that we are using the support vector machine or support vector model. This model, I will now fit. So I will fit my training data set with the two, remember the two features that I plotted earlier? So that those that I think they are the most informative features or variables that will tell me whether the tumor is cancerous or not. So is the mean radius and the mean concavity. And I will train it. So what's my answer? The answer will be the target column. So I'm just specifying. So in order to, if you want to know, so the 0s and 1, this is the column that is named target. If you have a different name for your target column, you just simply type it in the string. So I'm just here simply typing the column names. So the column name is the mean radius, mean concavity. So these are my two features, and this is my target. Okay, so after running this, it will tell me, okay, so I ran it with all these, you can always also like know what functions exactly, or what things you specified. So I'm using a linear kernel, blah, blah, blah. So you can change later on if you want to fit the data differently or use something else. You can know what did you do before, and or if you want to replicate or reproduce the exact same thing. So okay, so now we fitted the training. So we trained our model. We now want to inspect the properties of this model to get an idea how it performed. So you would just want to look at the coefficients and stuff. So how do we evaluate the trained model? There is simply also a nice way of just printing usually the most two things that we care about is the coefficient. So these are like the effect sizes or beta, and then the intercept. So if I print the SVM, since I saved, so remember I saved my model as SVM. So SVM, I'm now just printing the the coefficient and the intercept. So the first one I printed here is the intercept. So this would be the y-intercept of my line. We will visualize this soon, so you'll see it better. But this is simply my y-intercept of the line so I basically drew a line between my two classes, and the first one will be the intercept, and the second one will be the slope or the coefficient. So here's it's just typed. So here's my my coefficient, and if we want to visualize this, of course you don't always have to visualize, but it's always a good idea to see the things yourself, if you can.
What's the difference between double brackets and single brackets?
So you mean in the output?
And in the input.
Yeah. So in the input, so this is just this curvy like the curved bracket is just a part of the function, but I forgot what they're called. This is usually referring to a list, or you're specifying. So here the inside brackets is just printing the list of those two numbers, and yeah, you can check the different syntax in our early beginners Python introduction lessons. So there are different ways. So just don't want to go over time, but yeah, you can specify with if this is a list dictionary, or this is a part of a. So you have to make sure that you're using the right type of bracket for each. But in the output, you don't really care about the output. You just care about what you type yourself. So our next, so now we want to evaluate our model. So I will, and so I will just simply save. So I want to first evaluate, this is just for the plotting. So I'm simply trying to plot the equation. So I'm trying to do the line space. Let me just run it, and then it will be easier to say. So just run this cell, and then I will plot. So this is simply telling, I'm specifying that my x axis will, or the line along the x will be ranging from whatever two numbers. So these will be on the x-axis, the space between the line. And this is simply just saying, okay, the slope of that line along the y-axis will be depending on the coefficient. So remember, the coefficient is the slope of my line. So so this is the 0, 0. This is just the position of this in the list that was provided from my output here. So I'm just specifying, again, if you are not familiar, don't worry about it. We have other lessons for the syntax type of stuff, and they're all recorded on our website. You can always go and watch them. So I'm just specifying to visualize the line. Again, you don't need to do this, but it's a good idea if you want to see how your line is fitting. So I will just fit it. I will give it my intercept, so I know how the line would intercept and what is my slope. I'm just simply inputting those, and I'm saying that the line, it doesn't have to be like so long or so short. So I'm just specifying the features there. And the most important here part is like whenever now I'm trying to plot. So since I'm trying to overlay many plots on each other, so I'm just calling the subplots function. So I will plot when each line I will add, it will keep adding to the same plot. So I'm here just calling the subplots, and then I'm telling it my plot will be also a scatter plot like before, with the x is the mean radius and the y is the mean concavity. And my data, it's not the whole data frame, it's just the training. So as we have split it, and then the hue, the color will also be colored by the target, 0 and 1, or cancerous, non-cancerous, and the top. So this is nothing new. The second plot is I just want to use the line. So I want to annotate, like add the line. So I'm adding the line. Since I saved the line specs here, I'm just simply saying that my line is the x and y, and then k is just This is not a string in this time, or it's a string that's calling something specifically in the plot function. There's a lot of different options that you can color, have the line different, if you want it dotted, straight line, red line, black line, whatever. So this is just a simple black line, black straight line. And my label will be the SVM decision boundary. So what's your boundary for saying this is cancerous or non-cancerous? This is just typing a string label. And then my title for the whole plot will be the trained SVM on the model on the training set, just to let me know that this is the training set. And then please show me the legend, and please finally show me the whole plot. So I will run this. And as you see, it's the same exact plot that we have, but we're missing some points because or a lot of points because we split our data. And now we have added the line based on our support vector machine. So this line simply separates. And you will see that there will be errors. So there are some blue dots are the ones overlapped, or they're not really, so they're still on that side, and so the classifier may not perform 100% accurate or precise in classifying your two targets or two classes, but this is the model that I generated now. And so anyone still typing here? Okay. So this is just to illustrate like how do you visualize your training. The next important thing that we want to do, I can afterwards, if anyone missed anything, like we can always have questions at the end. So the next thing, now I trained my model on the training data, so I need to okay, we can try this quickly as well. This just to let you visualize also the decision boundaries. So this would be just a normal logistic regression. It will be that's it. If anything but beyond this line is non-cancerous, anything beyond this line. But the support vector machine also gives some decision boundaries. So it adds another layer to it. So here I'm just you don't have to type this. This is just to show you that now, I don't know if you see on the screen, I labeled them red. So here, red dot. So I just labeled them red. So show me the data points that are within the decision boundary that if you're in this boundary, you are classified as cancerous or non-cancerous. So it's showing me, instead of just one line, it's like a whole region that it's taking the decision upon this whole region. So here, just like for illustration, I'm showing you. So here, all of these are the support vectors. It's like the name of the model, and or the decision boundaries, and we can add the lines or the boundaries themselves. We can also add another line to show this. Let me skip through this. Okay. And yeah, I'll just type this here. So I'm just adding the two. So these are my boundaries. So this would be a nice plot to show in your paper with the decision boundaries. So just putting the lines there. So most importantly, now we want to know if our model performed well. So as I said in the beginning, we need to test your model. So predict using this equation, using this line, you want to put a new data points, introduce it to new data points, and let it predict is this person have a cancerous or non-cancerous tumor, and then I will correct this and check, okay, oh, this is right, this is wrong, this is how accurate and precise the model was. So to do this, I will use the predict function. So previously we used train when we were trying to train. So this time I will save my prediction on the variable as I will use the SVM predict. So the predict function, and I will tell it now use my testing data and also use the two features. And notice that I didn't specify the target. So, and it's actually a good idea to remove the target. So remove the 31st column so that it doesn't, like, if you want to be 100% confident the model won't cheat, but it's like, of course, it only does what you tell it. But I'm here only specifying the features. So I'm giving you X person that has a radius of A and a concavity of B. And then you tell me whether it's cancerous or not, or is it 0 or 1. So this won't do anything because I didn't tell it to print any coefficients or anything. So I can also do the coefficients and stuff, but I'm not really interested in all the coefficients and intercept. I just want to see the performance, or as we call it, the confusion metrics. Or the confusion table. So we can import this also from the sklearn metrics. So now I'm evaluating my model on this test data set. So I'm just importing the classification report and the confusion matrix. So the confusion matrix is simply telling me how many were classified as true negatives, how many were classified as false positives, were my true positives, and my false negatives. So it will just tell you the exact numbers that the model predicted. So I imported this now. I can just call so I will create my confusion matrix. So CM confusion matrix, I will create an array with the confusion matrix function, and I will tell it, okay, the test, now I will give it my target. So now I give it the answer. So you know who is exactly a true positive or a true negative. So based on this target, and then the Y predict. So the Y predict that I created here. So use this prediction. So what did the model say? So this is basically saying the first part is what it actually is, and then the Y predict is what did the model say or predict. And then I'm adding my labels, and then I'm putting this into a data frame, just like here, that like I'm showing here, but I just want it to be presented as a data frame so that you can even save it as a CSV later or any type. And I'm telling that this data frame contains my array, and the index will be is cancer is healthy, just like adding the column names and row names. So is cancer is healthy. So it's a 2x2 table, and then columns would be predicted versus predicted cancer, predicted healthy. And whenever you type the name of the variable as is, it will just simply print it out, like show it. So if I didn't type this, it will save it in the temp memory. Doesn't do anything like we have done before. But if I tell it, okay, now show me the confusion, the thing that I saved, so it will print out the data frame that I just created. So now it's telling me that 66 samples from my testing data set was predicted cancer and is cancerous. And 0 was predicted healthy and was cancerous. So our false positives were 0. And some were predicted cancerous, but they were actually healthy. So these must be, remember, within the boundaries. And 40 were predicted healthy, and they were healthy. So these are just simply the translation of the 2x2 confusion matrix. And finally, we can print the confusion report. Again, some people don't really do the confusion matrix and just print the classification report because that's what they want to report in their papers. So I just want to know my precision, my accuracy, and sensitivity, and all specificity, and all that metrics, which are basically calculated from this 2x2. And here I'm just showing the equations to calculate such, but you already have it in this report. You don't need to do the confusion matrix. So I'm simply calculating. So the accuracy would be my total positives, the true positives and the true negatives, divided by everything. And then the specificity would be the true negatives divided by the true negatives plus false positives. So meaning the actual negatives. And then the sensitivity is the opposite. So the true positives divided by the true positives plus the false negatives. So the predicted, so the predicted right. So it was predicted as true positive and it's right. And over the total of the correct answer, the correct positives. So whether they were true positives or false negatives that the model misclassified. So, so you can, of course, this is an equation. You can either do this yourself, or you can have it. So let's just simply, I will type this here. Oh, sorry. So this is just telling me, I'm just identifying from this confusion, since I already created the confusion matrix, so I can simply so I'm saving the true negative as from my confusion matrix, takes the 0 by 0, so take this, the true negatives here, so these will be my TNs, and then the false positives will be 0, 1. So these are simply the location. This is simply the location in the matrix, the false positives here. So I'm just specifying. And then, so this is how you would specify the exact location of something in your array or in your table. So I'm just saving each of them so that I can next calculate them manually if I want, by just typing these equations. And Python already knows how to do math without anything. So if I just type these equations as is and make sure the order of multiplication or division, or you just follow, if you're try to put brackets around the things that you don't want to be confused. And if I just calculated these as shown in the previous equation and told Python or to print all those 4 parameters, so it will tell me that my accuracy is 92%. So my model is 92% accurate, and the specificity is 1, and the sensitivity is 83%. So it looks like our model did pretty well. So another way to visualize it, which is also a more common way of showing this in papers, so is the ROC curve. So the receiver operator curve, and you calculate the area under this curve. So this is also a ready-made function from sklearn or scikit-learn. So I will import those 2 functions, so the ROC curve and the AUC. And then I will just tell it to I will tell it that my the decision, where from so I'm just specifying the test decision. Okay, thank you. And the ROC, so the saving those as variables as well. So the ROC curve, I wanted to have the target, so my final answer, and the test decisions from my radius and concavity features. And then these are just the plotting specification. So I want also subplots, and I want to plot the ROC. Again, you don't have to type this now. You have the code. You can try it always at home. But my point is, when you plot this, you want to see, so this is simply a plot of, like, the x-axis is usually the specificity, and then the sensitivity. So how well your model did in identifying like false positives, and how well your model did in identifying true positives. And if you want the best is 1. The AOC is always best in 1. So you want your curve to be as close to 1. So since we have, the AOC function is calculated our area under the curve of the receiver operator curve, and we have a 98%. So this is a very good, so by convention, anything above 0.8 is considered very good. From 0.7, it can be still fair, doing a fair job. Of course, depending on your type of problem, and it depends on a lot of things. But this is so we simply created a very nice, specific and sensitive model. So I think that's it for classification. So that you can have time to go into regression. So any questions in classifications?
So I have a question. So for the line space, like the evaluation X, like how do you define it to be from 11 to 18?
My evaluation. So when plotting the, 1 second, where was this? Oh, yeah. Yeah, so this would be based on your.
So why you choose it from 11 to 18?
That doesn't really matter. You can play along. So the 11 to 18 is simply showing that the line stops. It's in the space. It's between, on the x-axis is between 11 and 18.
Yeah, so you just try.
Yeah, it's just arbitrary. Yeah, you can play around. Again, this is just for your own visualization. You can manipulate this as much as you can. This is just from playing around. It seems like a reasonable space. You can make it shorter, longer. You can manipulate all these. But yeah, it's completely arbitrary. The most important thing is the coefficient. So the evaluate y, then I need the slope, because that's the actual representation of my line, the classifier. So then I need to make sure that I am using the coefficient that were generated from my training set. So I'm using the intercept and I'm using the coefficient on my y parameters. Okay. Any other? Okay. So let's now open the regression. So the regression also, if you go back to this page and you can click on the regression and then open in Colab, do the same thing. And connect, don't forget to connect. Okay, so we will also, since we're doing also the same, so we're simply, you can keep working on your same notebook, but just like it makes it easier if you want to save this later and know exactly what you did. But since we mostly imported everything that we needed for regression as well. So I will import the same. Since this is a new notebook, you would need to import those libraries over like each time. But if you're working on the same kernel, you don't need to do that. So I imported my libraries, and for this, I don't have a ready-made data set, so you can ignore the following part or you can follow along. So just like I'm synthesizing some data. So I'm just using creating some random data and specifying a bias and a noise just to make sure that it has some linear trend to it. So I'm just here creating this data set. And I will also use the plot style at Seaborn, and again, it's always a good idea to plot your variables. So here I just synthesized some random points, my X and Y, and then you can, if you plot regression or a scatter plot and see something like this, you might say, okay, I might see a linear trend there, or I might be able to fit a linear line in here, and you can see it's already like a positive trend. So that could be a good regression problem. So how would you want to, maybe we can skip. Okay, so let's go ahead and import the regression, the linear regression. So if you're familiar with R, it's just LM. So now, since I like R, so I will call it LM as well, instead of typing linear regression every time. So I'm just saving it as LM. And then I will fit this X and Y. Of course, is it okay to fit for my all data, all of my data at once? Pop quiz. Yeah. We should split our data into training and test. But here, okay, sure, you know this by now, but here I'm just fitting the my linear regression model on my whole data. So I just created a linear regression model, and it's time to see again. No visualization this time. I'll just jump into the coefficients. These, if you're used to regression, whether linear or anything, it's just like we need the beta or the estimates, and we need the we don't really intercept. So that if I just print the coefficient and intercept, it will also give me the coefficient and intercept. And next, I will, since we want to evaluate this model as well. So we want to predict new values. So I will simply synthesize some new points and let my linear model predict. So again, these are just well, we might as well visualize the model. So here, this is my regression line that I fitted into the synthesized data, and yeah, nothing really new here. So now I see that it's going into a linear trend, and now I want to show to generate, we use the predict the model. So to fit our model, we use fit, and then to predict, we use the predict. And now I will just add a predict a new. I'm trying to just generate and show the mean standard error. So I'm trying to predict a new. So here I saved. So a new data point with the error, and I want to just show the mean standard error and the other. So I will, if I just run this, it will show me the mean standard error. So you can also do the intercept by showing LM intercept. LM intercept. Oh, sorry. Yeah, this would be the kind of error if you have a syntax problem. And yeah, it's a straightforward equation. It's nothing, just like we would do it in R or in SPSS. It's just a different syntax, a different formatting. It's simply here that in sklearn, you just use the fit and predict functions. And if you want to split, you would use the same things that we did with our classification. And I guess we should have time to do this, or we can stop here. We have 10. Okay, so I can skip this exercise. We have 10 minutes to do the cross validation. So it's okay. So I want to show a nice cross validation. It is easy. Okay, I guess we can. So just a general, like I said, there are multiple types of cross-validation. So the one that we have been doing is the holdout cross-validation, which is simply splitting your data into training and test. So if I created a new data frame, and then I will also use the you don't need to do that, that's complex. So here I'm just creating the data. Again, we have already functions that does this. So here I'm splitting, so I created a data frame, and I want to, if I want to, you can randomly assign. So this is just one way of like assigning randomly or creating random split. So here I'm specifying that 0.6, so it's a 60-40 split this time. We can, yeah, I think we can skip this. So go to the key fold. Key fold is very important. So that's one way. You can split your data, whatever you specify, 30, 70, 30, 60, 20, whatever. There's another type, is called the key fold. So key fold cross-validation is simply telling you, so K is just a number. So you specify how many times you want to split, you want the data to be automatically split. So if I specify, so if I have 10 rows and I say split it, the K would be 2. So I want to split my data twice. And you can pick any number of folds, and usually for instance, if I have 10 data points and I specify 11 folds, so that's simply I leave one out. So if you want to train with 9 and test with 1, so that would be the K of 11. If I have, so 1 plus your number of rows. So if I have 10 data points and I tell it to split it 11 times, so that it will, first time it will skip the first one and take for example, the other 9. So 9 will be my training, and then the 1 would be my test, and then the next one will be put back this point and take the second point out, and then these will the 9 on the 9 will be my training, the 1 would be my test, and so on. So it will keep removing one by one point by the other, and so that's the I guess the most robust way. But you don't need to do a leave one out, but that's a way to do a leave one out. If you hear the term leave one out, it simply is just a K of 1 plus 1 more than your data points or rows. So you can, I think most papers are usually like 5 K of 5, K of 6. It depends. You can always like try different cross-validation, but I personally like the leave one out because it keeps removing point by point, so you have a better chance of detecting if one point was off or something like that. So it's a nice, but you can, this is usually by convention or an arbitrary thing. You can choose any number of folds that you want to split your data. So let's say we pick a K of 5. And then I will shuffle my data. And then we can set the range. Okay. this is, you don't really need to. And then, so this is the part that I want to get to. So now you can use the linear model and tell it to the train and test, and you can specify the calculate also the mean standard error by using the new testing and data set that you created from your folds. So this might be a way too complex way to do the splitting. But this is just one example, but I just wanted to touch on the general idea of how to cross-validate. So this is another way. It's a very popular, so I need everyone to know what k-fold cross-validation means. And again, instead of doing this, there's always a function. So there's already a function that's calculating the mean squared error, which would be based on all of our folds that were created. And you can, yeah, I guess the other two types are the penalized regression and the lasso. I don't think we have time to go through these, maybe for another lesson, but you can always work out the notebook. You have the answers, and I hope you got at least 10% of this session, since this is supposed to be a kind of intermediate level. But don't worry about if you missed, if you felt that you missed out a lot of things. But yeah, I think that covers the main concepts of the supervised machine learning. And any questions? Did you get at least 10% of the? Do you understand what machine learning is? Not really.
Well, I understand like the concept, but not necessarily the exact code behind it.
Yeah, of course. It's really hard. Yeah, I understand. It's really hard to specifically when they give such examples, complicating, so synthesizing the data and like doing all these manipulations that computer scientists would, okay, that, yeah, I know, like but for us, we don't really need this. So it can get, that's why I'm trying to, it's like, okay, you don't really need to know this. I didn't want to confuse people more. But yeah, it's just the concept that there is something called classification, something called regression, and how to select your features, how to see if you have what kind of problem, what kind of model would be suitable. Yeah, I guess just the basic concepts for now would be, I hope I was able to communicate that. Okay. Feel free to stick around. So we usually have the remaining half hour for discussion and coding. So exercise if you want to do. The lesson should be 1 hour. So I'm sorry I went over. But it's, yeah, if you want to do any of the exercises or stick around and do the code together, feel free to stay. But otherwise, please feel free to skate on the snow outside. Nice. Yeah, no worries.
So I have some CSV files,
Mm-hmm.
and I want to run like TCD or UMAP. Have you ever done that?
To create what? Sorry?
Like dimension reductions.
Oh, PC. Okay. Yeah. So Principal component analysis is one type of the unsupervised machine learning. So it's a type of clustering. So there are also packages to do that. So you can always go. Yeah, I should have referred to this.
I mean, you guys have never done
Yeah,
a workshop on that.
I think we did it once. Yeah, you might find the lesson. Yeah, I think. Yeah, you can scroll through our lessons. So UFT coders.
Okay, but this is the website for SK.
Yeah, they have a lot of exam. You'll find most of the things I explained today over there.
With code? With the code
Yeah,
provided?
with the code
Wow.
and the documentation. So
Can you just show me the
yeah.
website for
So okay. So
Yeah.
here's so this is, for example, the make regression one. It shows you what type of
Yeah. And it has data sets?
yeah. So
Wow.
it has already ready-made solution. So if you go, so here are the main types. So this will be the unsupervised. If you go to the clustering, I think you will find the PCA. You can also do PCA and R if you're more.
Yeah.
What's the? Okay, this is a K-mean. Yeah, we can definitely go do a lesson on the unsupervised one, but you can. Yeah. Bye. See you later. Yeah. Here. So.
Have you used TSNE or UMAP before?
No.
Not for biology, you didn't use it?
For what?
For like single cell data, but I guess you're not doing single cell.
Oh, single cell RNA?
Yeah.
Oh no, I have bulk RNA sequencing, which I haven't really touched yet. But here's the PCA examples. So this data set actually it's also a familiar one. Like it's well-known, the iris data sets, types of flowers. So yeah, but yeah, the RNA-seq I haven't really got into that. Like
Maybe one day.
yeah, I think was it Ahmed that did the RNA-seq maybe?
Who?
Ahmed, the president, UFT Coders president. I'm not too sure.
Anyway, it's great that you guys provide the code as well,
Yeah, for sure.
so someone can go home and like really dig into it.
Yeah. And there's a lot of other resources. Like there's so many people does similar kind of notebooks. We try to edit or make the examples more relevant. So the classification problem, like usually we find the example with something like this data set, which some people might not really relate into in the biology side. So we might like change something like this or look for other data sets. But yeah, there are a lot of examples and a lot of documentation resources out there. This library is amazing. Started as a Google summer project, and then it became a very widely used library. It's great. Yeah, scikit, the scientific kit. We might have look in this lessons and on our website. We might have a PCA lesson. I'm not sure if it was in R or in Python though. But yeah, if not, you can always try things like that. And then in our co-working sessions, you can come and bring your code and we can try work it out together.
All right, thank you so
Yeah,
much.
have a good night.